So now we are going to have a short session on the ultra-fast infrastructure. So first I will give a few words about the infrastructure, and after we have 3 talks, 2 from platforms and 1 from users. So Jean-Pierre this morning showed you the Operando infrastructure. Ultrafast is the sister ship of Operando. So you will find the same application protocol. You will find the same funding process. In fact, what is different are the challenges involved. So we had 4 challenges. The first one was to make attosecond and femtosecond sources accessible, and especially accessible to new users. The second one was to expand the wavelength range available in France, namely to go from XUV to terahertz in order to analyze new photochemical, new photophysical, and new photobiological processes. We have also the challenge to go forward toward time-resolved micro and nanoscopies in order to be able to analyze more realistic, more heterogeneous materials, in order to go up to the device, real device that, for example, are prepared by the Bordeaux prototyping facilities. And we have also the challenge to make more easily accessible the femtosecond micromachining tools, especially the one available in Saint-Étienne. So this translates now in 12 platforms. 7 are already available, 5 are expected next year. You have a large amount of investment associated with this new infrastructure, so 3.6 million euros in order to update or to upgrade the platforms. And we will have almost 3,000 days available for the whole project, which translates in about 400 projects that can be submitted. We count about 7 days per project in average. So a few examples of the update and upgrades that have already been made. So you have many more examples on the posters. Maybe you went to look at them during the lunch, but you still have the coffee break next to go and discuss with the people from the platforms. And of course, most of these platforms deal with pump probe experiments. So I tried to make a summary of the probes that are now available. So we have a strong effort on vibrational spectroscopies. So mid-infrared, far-infrared spectroscopies. We have also femtosecond Raman that will be presented by Manuel. We have femtosecond optical microscopy, near-field measurements. We have also picography in LIDIL. And we have also a system dedicated to gas phase measurement with VMI and AZMS. So the application process is the same. The portal is the same as the one that was presented this morning. So now I give the floor to the science, on to the technique, with Manuel, who will present you first the femtoraman.
Thank you. Okay. First of all, thank you very much to the organizers for giving me the opportunity to put in the spotlight the femto-Raman platform, especially because Raman is a technique that everybody knows that exists, but nobody uses. Everybody thinks that it's quite difficult, and then if we do femto-Raman, I'm pretty sure that none of you think like one of the techniques that you can use to characterize your samples or to work on your samples. So I hope that after these 5 minutes, at least you can consider, and then you can come to talk to us. So the platform, it's the visible, oh no, where is the laser? Here. The visible face of the platform is Bruno Robert, but we work very tight between him, myself, and Juanjo Romero, that is a young scientist that we hired recently, and also he will give a talk, I think, tomorrow. So we are located there at the I2BC, and basically we use this platform to look at the vibrational modes of the excited states. That means states that they are living very short. We have a temporal resolution around 150 to 3 nanoseconds, and we can cover quite a wide spectral range, although visible is the most visible at this moment. Okay, so what is interesting about this? Well, to do Raman, we need a very narrow lasers in order to prove each one of the different vibrational modes. The problem comes that when we go to very short times, like femtoseconds, basically, due to the Heisenberg principle, we cannot reach such a narrow bandwidth. So basically, we have a time limitation. The technique, basically, if you know transient absorption, normally pump prof, is normally an actinic pump that excites the sample, and then we prove the sample with a supercontinuum. What we do here is to avoid this. Basically, we excite the sample, and then we have a Raman pump that is spectrally narrow but temporally wide in picoseconds that is giving us the spectral resolution and creating the Raman modes. And the Raman probe that is temporally narrow, and basically these two beams interact coherently, and they enhance the Raman modes, giving both temporal and spectral resolution. What is that interesting for? So that is especially interesting for samples that they are very complex, or that they have very excited states evolving at the same moment. Biology normally is the most complex things. So that will be, doesn't matter much, but it's a photosynthetic antenna, and they have plenty of bacteriochlorophylls and carotenoids. And we know that once a photon is absorbed there is plenty of different processes happening in parallel. Plenty of people have been studying that. There is a lot known about this, but basically still is not figured out how the energy moves so efficiently through this antenna. So basically the idea of this technique is that that will be the transient absorption spectra, and we know that everything is happening there. So we can get this Raman probe, and we can subselect and make different selections of parts of the spectra. And we prove specifically each one of the excited states that corresponds to this absorption. What we end up having is basically for each one of the Raman probe that we put, different spectral maps with change the vibrational mode within time. And we can do that for different Raman probe. That gave us selectivity. I don't need to explain exactly what is one of these spectra, but you can see without knowing anything about photosynthesis, even about Raman, that clearly for each one of the different maps, we have different vibrational modes. And we also can see how each one of those vibrational modes can evolve with time. We do that with photosynthetic systems, and it's quite nice because we are able to separate specifically each one of the vibrational modes without any kind. That is just raw data, so there is no any kind of analysis. Of course, later we can do some kind of modeling and even improve it. So the idea is that we can do that with very complex models. We can do that also with artificial systems. Juanjo will show you some of the data later. And ideally, you have to start considering that Raman is a technique that sometimes may be a little bit difficult, but can bring a lot of information. So I will encourage you and also your students to come talk to us, see if this technique is right for the science that you are doing, and let's see if we can make some nice measurements. Thank you. Yeah.
Thank you. Yes, I think it's a very nice demonstration how you can selectively get the Raman spectra of different chromophores there. What is the ultimate spectral resolution?
spectral resolution at the time resolution, or
no, really in the spectra, the
spectra,
the Raman spectra.
Around 3 wave numbers, 3, 5 wave numbers. That depends if we are looking at the UV part or at the IR part.
Okay, because the looks rather like 20 wave numbers in the spectra you show there.
Wait. The width of the vibrational mode depends a lot of what and the spectra that we are looking at, and also that is done at room temperature. We know that when we go at low temperature, we can get better resolution. Sorry.
Thank you. Should I continue in French or in English? Okay. Thank you. So I am Benoît Cluzel from ICB. Where's the laser? Sorry. From ICB in Dijon. So we are newcomers in the PEPR LUMA, since we are a new platform that you will have access to, hopefully. And I would like to mention first that SMARTLIGHT is first an Equipex Plus project that we are implementing together between ICB in Dijon and femtosecond in Besançon. And the goal of this Equipex Plus project is to build a French infrastructure devoted to optics and artificial intelligence, and the different manners optics and artificial intelligence take benefits together. So this is a picture we propose to the international jury, and actually we are implementing more than 20 projects dealing with artificial intelligence optimization of existing optical systems, optical materials, and on the contrary, how to fabricate photonic hardware to implement a new generation of photonic computers which are faster and more energy efficient. Now, this project is an open research platform you have access to, and we have implemented different facilities which are sorted in 4 technological clusters. Each of these clusters are addressing some specific technologies. The first one is related to high-speed optoelectronics, and I'm just putting the spotlight on the best feature we can propose and which are almost unique in France. So in optoelectronics, we can address optical and electronic signal in real time at 1 gigahertz rate, which means that we have a 10 picosecond real-time resolution to monitor optical signals. For the multimodal microscopy, we can achieve sub-wavelength resolution up to 10 nanometer on nanoscale devices such as plasmonic devices or any other nano-optics nanostructure. On the third cluster is about 3D optics. So we have some facilities to fabricate fibers with a local specialty on mid-infrared fibers made of chalcogenic glasses, which are highly transparent in the mid-infrared. And we have newly installed a 3D lithography system enabling 3D printing on fibers and any wafers, and also realignment capabilities on photonic integrated chips. And the last cluster is hosting all our femtosecond laser line, which are very different depending on the application we are playing with. I mean, in terms of repetition rate, we are ranging from the kilohertz range to the megahertz range, and we are covering UV to mid-infrared up to 16 micron. So I will not explain all the equipment we have on the platform, and if you want more information, please visit our website, and we will have a full detail of all the equipments in the different clusters. And if you visit the website, this is also good for our referencing on Google. I will just finish by putting the spotlight on one illustration that we made recently, and which may be of interest for some people here who are playing with chirality and plasmonics. And this is a near-field image of a gold nanodisk, which sustain a dipolar mode resonance. And this is the near-field images of the complex field of this nanodisk, which is made by near-field microscopy, implementing an heterodyne detection. Basically, you have a sample, you shine the sample with a laser, and then you scatter the local field with a probe. And you make this scattering interfering with part of the incident lights. So this is an interferometer. You put that on a lock-in amplifier, and you manage to extract the amplitude and the phase of the optical field. If you excite this, as usual, with a linear polarization, you have a nice picture here of the dipolar mode, and with the phase shift and the phase jump in the mode. But if you move to a circular left or circular right polarization, then you're able to excite a vortex. And probably this will be of interest for people working on chirality. That's it for me. Thank you for your attention.
What is the dark circle in your?
Oh,
what does it correspond to?
Yeah.
The small one, yes.
Well, this is because there's a double topography step. You have the big disk, which is on a small pedestal of silica around, which is under-etched.
Okay. Thank you.
So don't hesitate to get in touch with me during the coffee break or in front of the poster.
Thank you. Thank you. So the next speaker will be Sylvain Betoule from LCPMR, who will speak about his experience as a user in CELIA.
Yes, exactly. Hello, everyone. So Sylvain Betoule, and I will present you the experiment we did at CELIA at Bordeaux, because our motivation was that we have another experiment that is planned at Soleil Synchrotron, and we want to study the iodocan-4 here in Corchel at Synchrotron Soleil. But the sample we got of iodocan-4 from a company was not really characterized in terms of enantiomerical excess. So we wanted to characterize, and so we used the LUMA funding and the platform at CELIA to characterize it, and by the study of the photoelectron dichroism of the iodocan-4. And to do this, we needed a source in the visible range for 515 nanometers. And the analyzer was a VMI spectrometer that can measure the kinetic energy of the electron emitted and resolved it angularly. So the beam time was of 1 week at CELIA laboratory. Many thanks to the host team that prepared all the setup 2 weeks before, so it was really helpful for me. And then all the acquisition and the analysis was done in collaboration also with the host team and with my team at the LCPMR. So first, to explain you what is photoelectron elliptical dichroism. When you ionize a chiral molecule by a circular light polarized, you will see an asymmetry forward-backward in the probability of emission of a photon. And this asymmetry is along the axis of propagation of the light. We can describe it by the G function that just do the difference between intensity forward minus backward, and then renormalized. And so this is what is interesting is that when you change the enantiomer, you have the exact same amount of asymmetry, but opposite sign. And this is also the case when you change the left polarization from a right polarization. So now, what about elliptical polarization? So we can describe the polarization state with a third parameter of Stokes. When it's -1, your circular left, then elliptical, 0, your linear, elliptical, and 1, your circular right. And we could assume that there is a linear dependency with the amount of polarized, circular polarized light. And this is right, but when you are in one photon ionization. the experiment we did, we were in multiphoton ionization with a resonance state here. And when you're in that case, you can see something that is not linear, that can have here a maximum for an elliptical polarization. You can see also a change of sign there. And so this is interesting because you add a degree of liberty here that can give you this kind of spectrum and that is really sensitive to each sample, as that give you a probe for analytical chemistry. And so this is why we use this technique to characterize the iodoconfor. So here, as the first result, we studied the iodoconfor, we compared it with the confor, and if we just first focus on the iodoconfor spectrum, we can see that our sample plus and minus are well reversed, so we can determine a relative enantiomerical excess between both samples that is close to 1, so no, we are confident to use it at synchrotron Soleil. And what was pretty surprised is that when we look at the confor spectrum, it was really different from the iodoconfor, so that shows that this technique is really sensitive. And so now we want to pursue also in this way this measurement and to try to explain why it is so different. And so there is another LUMA project that was accepted that will help us to investigate these differences between both behaviors in terms of photoelectron dichroism. So thank you for your listening.
Thank you. Do you have some questions? I have only one question. What beamline will you use on Soleil?
It's a Pleiad, so the goal is to be in the range of iodine core shell, and so it's around 30 eV, and so Pleiad can go between 10 and 1,000 eV, so this is why we used Pleiad.
So you have an overlap with CELIA in terms of energy?
Not at all. So that's why if we had an overlap, we could do this experiment at Soleil. No, CELIA it's more at 515 nanometers, so it's more 2 eV. So it's a bit less than the minimum range of Soleil. And at CELIA there was also all the setup with to measure this kind of spectrum that is not at Soleil. That is also an argument.
Thank you. Other questions, or everyone is going to see the posters, of course, and maybe take some coffee. Thank you.